Hello, everyone. I'm Eric Hyam, Technical Editor with Microwave Journal, and thanks for joining us for this latest Microwave Journal online panel session. We've got a great session lined up today. It's entitled The Future of Military Radar. But before we begin, let me cover a few logistics. If you'd like to download the few presentation slides that I'll go through, you can find a copy in the handouts window. I've got questions teed up, but if anyone in the audience has a question, please type it into the Q&A window at any time. And the presentation is being recorded, so it'll be available to watch again and recommend to your colleagues. So let's get started. And I'd like to do that by spending a few minutes framing the discussion with some thoughts on the topic. Okay, so here's some data from a defense electronics forecast I did at Strategy Analytics, and it looks at the electronic segmentation of the big three, radar, electronic warfare, and communications. Now, it's important to note that this focuses on the electronics in the system and not all the other peripherals. So while the total of about $90 billion in 2030 is large, there's actually much more money spent in each domain. So this is a session about radar, and that's actually the smallest segment, with roughly speaking only about 25% of total spending. So that's interesting. But if we use a different filter, we get this slide, which looks at the semiconductor content in these three segments, and that's a much different story. From a semiconductor revenue standpoint, radar is the largest segment, accounting for slightly more than half of all semiconductor revenue. So why is that? Well, AESA's active electronically steered arrays have really become must-haves for military programs. They add significant flexibility and performance, and these arrays have lots of elements, all fed by RF modules. So lots of electronic content, but not as much enclosure, connector, cable, and other content. And that's what changes the view. And that semi-content includes lots of digital and RF silicon, along with GaN and GaAs. So just to put a finer point on the radar market, land and airborne applications dominate the market, accounting for about 75% of the total electronic systems expenditures. Slicing the data a bit differently, surveillance radars, which map closely to ground-based applications, and fire control radars, which map closely to airborne applications, account for an even larger share, reaching about 80% of the total electronics expenditures. And that's important because, as mentioned earlier, the trend is towards solid-state AESA radars. Now, not everything is active, but that's the trend. And why is that important? Well, as the block diagram shows, lots of electronics, both digital and RF, in an electronically scanned array. Potentially, each radiator has a transceiver chain behind it, so you get that multiplicative effect, as large land-based arrays can be into the tens of thousands of radiators. And the trend is to do more with less. Expand your capabilities, but do it more effectively. So this is driving a reevaluation of strategy in the US, and to this community, that means more sensors, more disaggregation, but higher performance and functionality. So that's everything from technology to packaging to test and onto software and control. So that does and will continue to present challenges and opportunities. And we may not talk too much about hypersonic weapons, but this panel is about the future, and they've been in the news recently, but mostly from the offensive standpoint, the weapons aspect. Defensive capabilities that are essential to maintaining that balance between threat and response are seeing lots of development, and those efforts will rely heavily on radar. So expect those issues to start percolating to the surface. So with that, I've teed up some of the topics that we'll be discussing, and let's get started on that. We've got a great panel of industry experts. So let me start by getting the panelists to introduce themselves along with a short description of their companies. So let's start with Rodger from Mercury Systems, and then we'll go down the list that you see here. So Rodger, if you don't mind getting us started.
All right, Eric, thanks for the introduction and glad to be here. Most of you are familiar with Mercury Systems. Mercury does provide a wide range of products that implement just about every part of the signal processing chain, from the antenna all the way through extensive processing, recording, and other destinations of the data. So I am formerly of Pentech. We were acquired by Mercury in May of 2021, a little over 2 years ago. So we're bringing specific expertise from our division with FPGAs, high-speed A to D, D to A converters, all in open architecture form factor products to serve primarily military markets. So we're very interested in taking advantage of some of the other. Sorry, I just heard an echo. Okay, we're very interested in taking advantage of other parts of Mercury, which include MMIC devices and other processing capabilities that Mercury offers. So I think with that, I'll pass it along to Tim.
Great, Rodger, thank you. And yes, Tim from Rohde.
Yes, good morning, everyone. So Tim Fountain from Rohde Schwarz. Rohde Schwarz is celebrating its 90th year this year. We're based in Munich, Germany. We are still a private company owned by descendants of the founders, and we specialize in high-performance test and measurement equipment for a number of different industries, including the aerospace and defense industry. I am responsible for our market segment for radar and EW. I've been in the industry working on RF systems for more than 35 years. Over.
Great, thank you, Tim. And last but certainly not least, Peter from Analog Devices.
Yep, I'm Peter Loss. I'm an RF engineer in Analog Devices in our North Carolina location. So I work side by side with a lot of the IC designers, the high-speed data converters, RFICs, and then our application engineers as we bring these into the world, and then also supporting the marketing and the future needs that we need. So we have a lot of unique things here. As we go back to the block diagram, we may refer back to that in some of the questions, but we make parts that go into all those. And so those of you that have been around for a few decades, you know the analog devices from the converters, you knew Hittite from the RF pieces, you knew Linear Tech from the power, and now we have Maxim also. And so all four of these legacy companies are under one roof with Analog Devices. And so it's really a unique platform with top-notch EEs of all sorts. And we're pressing onward into the sort of direct sampling. And we're at IMS last week, and if any of you were there, or if you just saw some of the announcements, we've enabled X-band direct sampling. And so we'll talk about that over the next hour as we get into some of the things. But those are the things we're doing, and we're really trying to push the swap and the higher speed and enabling customers like yourselves to do the types of arrays that you're looking for. I'm going to pause there. Thanks.
Great, thanks, Pete. So we've got questions rolling in already. That's great. Please keep them coming in. I'd like to start this off, though, and let's go down the panel on this one. Sort of that 50,000-foot view. What major trends are you seeing in radar technology today? And Rodger, let's start with you, and then we'll hit Tim and Pete.
Okay, thanks. Yes, I echo your earlier comments about phased array, AESA. It is incredibly important because just about every application of radar, every radar application is taking advantage of phased array technology. So it's very important that we and our silicon partners, like Analog Devices, for example, takes extreme care to ensure synchronizing each of the channels to make the beamforming and processing to do the phased arrays possible. It's not easy, and the more elements you have in your array, the more difficult that can be. But it is an extremely powerful trend, saving a lot of the mechanical structures that previously were required to turn an antenna or aim an antenna, which is really very, very difficult in an airborne or a small UAV platform where you just don't have the space or the weight to be able to do those things. So I would say that's the major thing. The other part is extreme processing capabilities to take more advantage of the sensor signals that are acquired, and that includes a migration towards artificial intelligence to try to extract more actionable information from the data streams that are coming in to make our warfighters more capable of making more well-informed decisions faster, more accurately than they could without that artificial intelligence add. It's still new, but it is definitely a growing direction. So phased arrays definitely, artificial intelligence, and the last thing, which also Peter mentioned, is direct RF sampling, which means data converters that can directly sample signal frequencies that are way up to 30, 40, and higher gigahertz to eliminate the often bulky down converters, analog RF down converters that were previously required to move those signals down to a lower signal frequency for A to D converters operating at that lower frequency. So those are the major trends that we see.
Great, Roger. Thank you. Tim, from the test and measurement standpoint?
Absolutely, yeah. So I'm going to break it down into 5 different areas and then just cover a couple of different things in each of those areas. So under general trends, higher bandwidths, they're driving test requirements moving from 1 to 2 to 4 to 8 gigahertz of instantaneous bandwidth. The convergence of radar with electronic warfare and comms, it's really hard to split apart what is an EW system, what is a radar system. Multifunction radars that can accomplish many different things at the same time. Frequency agility on the radars, hopping around so they don't sit on any one frequency. That again drives some of these huge bandwidth requirements for test systems that need to be able to watch where the radar hops. Higher operating frequencies of 40, 60, and even up into the 90 gigahertz range. Roger touched on this. One of the things that's driving artificial intelligence and machine learning at the tactical edge is the need for these systems to be able to counter threats that they haven't seen before. And that can't be countered with traditional static library approaches. We talked about the increasing channel counts and the number of elements in some of these modern systems. To give an example, the AN/SPY-6 AMDR radar has over 5,000 elements per face, and there are 4 faces on a typical ship. So that's more than 20,000 elements in total. We talked about direct conversion. So one of the things I'm going to say on the direct conversion is we have this huge bandwidth, and that's both a curse as well as a benefit. What I mean by that is that if you have large emitters in the environment and you have a huge wide bandwidth, it's very easy to overload the front end. So we've really moved the problem of wide bandwidth and direct conversion into how do we filter front ends so that we can address the signals of interest. And there's things like the DARPA WARP program, the wideband adaptive RF protection, which seeks to develop some novel techniques around filtering to enable these direct conversion systems. Over the horizon radar is having somewhat of a renaissance, especially as we have these new, air breathing hypersonic missiles. The desire to, be able to detect those missiles at longer range and over the horizon is driving that. Also, jamming immunity on over the horizon radars. Spectrum sharing is a huge issue. There are lots of competing users for the spectrum, and we're still trying to figure out how we can share and coexist between military systems and commercial systems. And then the last one I'm going to cover really is there's a renewed interest in passive radar. The fact that traditional, monostatic radars have illumination, that means you're a target for an adversary. If you can use emitters in the environment, you can hide in plain sight and use those. And, improvements in DSP, as well as illumination from some of these large satellite constellations that are being put up, are offering some tantalizing opportunities to renew technology in passive radar. So that's 5 different areas that I'm seeing some growth in. Back over to you.
Great, Tim. Thank you. And Pete, from ADI's perspective.
Yeah, that was actually, I really enjoyed Tim's summary there. And maybe I can just build on that. Is it okay to go to the block diagram slide? Can you flip over to that? And we can use that as a way to visualize the trends, kind of from what the electronics are. So one unique thing, I guess, for the listeners, like our companies don't really compete against each other. We work together. With Rohde, we use their test equipment. It's all in our labs. They use our parts. Same with Mercury. They use our stuff, and then from there it goes into things many of you would use. This diagram can probably be well used I was glad to see it's copied out of one of the ADI notes, and we can use it to kind of articulate some of the trends. So what is this showing us? It's a generic block diagram of a phased array, and it's got a lot of simplifications in it. But it starts from the right to the left. It might be the easiest. Come in from the antenna, and you have TR modules, and so that piece is always going to be there in these arrays, and the TR modules have to fit within the lattice spacing. So the lattice, typically you're in a half wavelength, and so the size is very challenging as you go up in frequency. As Tim mentioned, we're going up 40, 50, beyond. And so that's going to drive trends in miniaturizing the TR modules and the PAs and the LNAs that go behind there. So that's an obvious thing to need. Now, for a radar, you want more power to come out. So higher power, more efficiency, being able to get the thermals all in that piece, it is a trend. So that's coming. Now, going to the right, the next piece of the block diagram is in the analog beamforming layer. And that's sort of an optional layer depending on how the system engineers. So if it's every element digital, that goes away. But if it's all analog, like the piece all the way at the left goes away. So there'll be trends as we try to go more and more every element digital. The physical constraints will limit how high in frequency we can go every element digital. And we mean, just mankind as we try to develop these things. So there's going to be, in our view, an analog beamforming layer that stays for some period of time. And whether it's the 4-to-1 subarrays or 16-to-1, it's up to the system engineers to partition. And so we're going to continue pushing those types of parts out, even in parallel with pushing the data converters to higher and higher frequencies. All right, going over to the next step to the left is the RF up-down converters. So as Rodger said, as the data converter speed goes up, that can be completely eliminated. And for size, weight, power reasons, there's desires to really just completely eliminate it, come directly into the data converters. If you look at the state of the data converters, so S-band direct sampling has been done for some time, I think before COVID. We have parts that do that, our competitors do, and many of those are out in the world. The next quest is to push the data converters up to X-band direct sampling, and so we've done that, and have an announcement out, and those parts will be commercially available. Our view for some of the other things that Tim has described is to maintain the high dynamic range. Now, there's always a quest. You hear these trends and a lot of industry discussions of what can you give up for dynamic range versus power and versus speed. But when push comes to shove, because of the amount of interference and some of the struggles in the tunable filter technology, people generally need the dynamic range. And we've almost never heard a case where, well, we got too much dynamic range. It always can be used to some type of benefit. So that's a type of thing to watch as the converters get developed. And then for the wide bandwidth fast hopping, the next layer down is the digital up-down converters. And if you want to do fast hopping, that's really the way to do it. You have a wide bandwidth right in the converters. The digital NCOs can move very quickly, just limited by the control infrastructure. And then on one clock, blam, they're at the next frequency. And so that's really the best way for fast hopping. And then you see all the way to the left the digital beamforming layer, and there'll be, that right now it's typically in the FPGAs, but there'll be ASICs developed there. It's people that do high volumes will do that. And so as you map out the block diagram that is used kind of generically in any of these systems, I think you can sort of use that to visualize some of the trends. And yeah, so maybe I'll pause there and pass it back to Eric.
Yeah, great. Thank you, Pete. And I think that really does a great job of kind of shining a light on trends and some of the challenges and some of the opportunities. I do want to point out that we had just barely gotten about 10 minutes into this webinar, and I probably consumed 5 of those minutes before we mentioned artificial intelligence. So, and I'm being a bit facetious here, but I think that's important. And I think that that's definitely a trend that everyone is working towards going forward. So that was that 50,000 foot question and answer, as I mentioned. If we go to the audience and grab some of those questions, it's a bit more tactical. So the first one that I have from the audience is, can you use a VNA to measure phase shift within a radar receiver? So Tim, maybe can you start us off with that one?
Absolutely. If that person who asked the question is interested in more details on that, we have a lot of white papers on using VNA in all parts of the blocks that make up a radar. So we can delve into more details on that. Absolutely, though. The answer is yes.
All right, thank you. Another one from the audience. And for the general panel, whoever wants to jump in on this one, what is the role of reflect arrays in the future of radar? We generally believe that if you can afford to use a phased array, you probably should, but reflect arrays seem really useful when you can't afford the complexity or power consumption of phased arrays. In the context of the future of radar, is there a path forward to reflect array implementations? Whoever wants to jump in with that one, please feel free to do so.
All right, I guess I'll take a shot at it. Unless somebody else wants to go first. So I'll give you a perspective. In my view, many things will exist in the future. And I get the question a lot, particularly at AEI, like, what's the block diagram for a radar? And it's like, wow, like what's the architecture for an A to D? How is this? There's many ways things can be done. And so depending on frequency, depending on cost, depending on power constraints, there will probably be a home for things that were always done in the past, as well as many variations of what will be done in the future. In my view, the every element digital quest will continue, so that will be one, but not everything's going to go that way because it's expensive. It's a lot of work. There'll be things backed off to hybrid systems where it's a combination of analog and digital, and then there'll be all analog arrays for when you need a single beam and a single direction. That'll exist. And then when you just want a single waveform generating receiver, there'll be rotating dishes. That will still exist. That's not going to completely be eliminated. So in my perception, all of those can exist and will probably be needed and will be optimum for certain applications. And then it's up to the engineers and the businesses to decide what's the most economical within the resources you have and the time and what's needed for the application.
Yeah,
Thanks, Pete.
yeah, good point. Go ahead, Roger.
Tim, why don't you go ahead? That might have been me.
Okay, I'm sorry. Yeah, so reflect arrays are an interesting technology that's been around for quite a while, and they address some of the issues of parabolics, but they still need some steering. And one of the things that I'm seeing as a trend or as an interest is potentially using some of the metamaterials in a reflect array antenna to basically, steer the beam by changing the properties of the reflector itself. So I think that's an area that is still being looked at. I've had a couple of discussions over the years, but I guess for me, reflect arrays are still somewhat useful, but they don't address the size, weight, and power issues that are driving a lot of the larger phased array antennas, because the horn still needs to sit, somewhere quite a ways away from the actual, array itself. So the main use I've seen for these has been on satellites, where physical space isn't such an issue, and they still have their uses there in terms of, being able to, create a similar effect to a parabolic. So yeah, over to you.
Great, Tim. Thanks. Another audience question. Please comment on alternative phased array architectures for supporting wideband waveforms over large aperture arrays. That is addressing the true time delay question. Peter, can we maybe start with you from the analog device standpoint?
Yeah, I'll start there. Okay, so if we thinking about a way to articulate this. All right, so the ultra wideband waveforms, there's a need for true time delay, as was added in the question. And what happens if the beam is steered with only phase shifts, then the phase changes as a function of frequency, or the delay change is inconsistent with frequency. So when a wavefront hits the side of an antenna, if it's wideband, there's a time delay difference across the elements. And time is a linear phase versus frequency. That's probably the easiest way to visualize that. So that leads to the need for a true time delay. And actually, as we look at this block diagram where it shows the analog beamformers with phase shifters, that leads to an error. And that error is well known. It's published, and it's typically called beam squint. There may be other words for it. So in our case, we are supplying two types of methods for doing this. So when there's in every element digital subarray, then it's much easier to do true time delay, and it can be done in the digital domain. And you don't have to just delay by a clock. You can delay by fractional clocks, and that's how it's done. And so that's a type of option. In the analog beamformers themselves, we are making true time delay beamforming ICs, and so some of those have been released. We can talk to anyone specifically interested. We can get you a separate brief on what those parts are. And so those, from the semiconductor view, that's efforts that are in place now to kind of enable to help with that problem. And I think when you're doing an architecture, there's a combination of the subarray size and then what's true time delay and phase shifts that can be used to mitigate those as you look at the antenna patterns. The MATLAB phased array patterns and other CAD phased array tools are actually very good at modeling these types of errors.
Great, thank you. Any other thoughts on that one?
Yeah, I mean, at the end of the day, you can't break physics. The array is going to start degrading in performance as you move away from the optimal lambda over to spacing. And as Pete was saying, the concept of beam squint is well known. There are some ways of mitigating it, but at the end of the day, you got this physical attribute of the array that as you get to these really wide bands, that starts to become an issue. Sure.
Alrighty, great, thank you. How's the shift to phased array radars affecting the system architecture, and what implications does that have on device and test technologies? And maybe Rodger, can we start with you from Mercury's standpoint?
I'm sorry. Could you repeat the question, Eric?
Sure. The shift. How is the shift to phased array radars affecting the system architecture, and what implications does that have on device and test technologies?
Well, I think there is a significant trend towards moving more of the initial acquisition and pre-processing up to the edge, which means very close to the antenna. And so the idea of having many elements, both receive and transmit elements in an antenna, means that there's a lot more that has to then go up close to the antenna, which is optimal because you can then save a lot of the signal loss and fidelity because you're digitizing very close to where the signals originate and where they leave. So I think a lot of the phased array impact has been, how do I reduce the size, weight, and power of each element's electronics? And how can I have a more highly integrated, smaller footprint per channel? And so that has tended to be an increasingly more important metric for any proposed architecture that goes forward. And I think we're going to just see more and more of that trend. There's been a lot of integration of function, not only in the advancement of the data converters and FPGAs and other parts, but also in the RF circuitry, where Mercury, for example, has a MIMIC facility that does an extremely good job of making monolithic microwave ICs that can do adaptable filters, movable filters, adjustable bandpass filters, which is really great, especially for the direct RF technology that is also a significantly growing trend. So I think that's my answer for that particular comment. Yeah.
Great, thanks, Rodger. Tim, from the test and measurement standpoint, how are the phased array radars affecting what you folks are doing?
Oh, absolutely. Yeah, great question. I love this question. So, we already talked about the density that's required for some of these. Really, when we talk about phased array for us, we're talking about the TR modules that sit behind, the front end of these systems. The increasing complexity of these front ends leads to really long test and calibration times, and is really driving a lot of desire to try and reduce the test time. The TR module itself is evolving from what used to be a connectorized analog in or RF in and RF out, just really a frequency converter module, to a complete system on a module, including a digital back end and an integrated antenna. And when you get to that point that the antenna is integrated and the digital is, it's digital in and out, as some kind of SerDes link on the back end, you got to change your tests. And the way that you do tests in the past is not the way that people are wanting to do them now. When you have the antenna integrated, you need to move to an over-the-air test. You only can basically communicate with that TR module by positioning an antenna in front of it that basically, interacts with the antenna on the actual TR module. So that those are all driving, an OTA and actually positioning an antenna across the phased array. If you're doing a system level test and calibration is also part of it. You want to reduce side lobes and all the other things that come along with phased arrays. Frequency and phase calibration. All of these things take a long time. The second part, and this is sort of really just delving a little bit into what Rodger was saying about the integration of mimics, is in the past, you would be able to take that module and create test points within the module to, look at how the module is performing at various sub-elements or sub-blocks of that module. And these days, that's not really possible. It's integrated, it's hermetically sealed potentially. And so you have to test it at the system level as a complete, sub-assembly rather than being able to look at individual test points. And then, I'd say the last part is that the density of these modules is driving cooling, and size, weight, and power always are a key consideration. So, it has not, the integration has not improved the ability to test these. There's more to do in less time, and it's a more complex test with different test requirements. And of course, then finally, I'm going to say customers are moving away from traditional pulsed or maybe simple modulation schemes to much more complex modulation schemes. As I said earlier, customers are looking at these radars to potentially encode communication. For instance, if it's a missile radar, it might be sending targeting information as part of the radar itself. And that requires more complex modulation. So you're typically going to be moving from a vector-based approach to more of a scalar, where you can do more complex modulation tests, and that also is complex as well. So yeah, it's a huge challenge, and I'm pleased that question was asked. So back over to you.
Great, thank you. Pete, any thoughts from your side?
Yeah, I'll just add to it. Tim brought up a kind of a wide range of things to think about there, and so one of the, I would say, trends or growing in the profession is, if you think about the receiver, it wasn't long ago you'd break out the RF metrics, gain, noise figure, TOI, and you have a data converter, and it's NSD and full scale dynamic, full scale levels, SFDR with that. And so, but you don't have access to all these pieces anymore. And so you can test them or simulate them as individual pieces, but then people have to think in terms of, all I got is a stream of digital data. Is the data what I expect it to be? And so we've tried to put out some app notes on how to think about that. And depending on how the digital processing is set up, there's a whole nother complexity that's added. So in the system budgets, you have to be able to kind of visualize going from, out of the air where you have power and waveform that comes in at some power density that turns into, signal into the LNAs. You have the whole RF front end, gain, noise figure, linearity. You have the data converter specs, and then any digital processing. Typically, we try to characterize them with like 0 dB gain and really not modifying anything, so we can characterize from A to D up through the front end. It's valuable if you can test, at least be able to sort of bolt on your antenna and have conducted evaluation into the receiver. So that's a whole piece that's coming. It's already here now, but being able to visualize that and getting engineers that can quickly see where the choke parts are, and then for swap, where can you relax? Where are things over designed so that you can relax power and where you can, and then rapidly test these, because test time can take a while. The calibrations are a big worry for people, and some of the digital processing there can be as much processing put into the calibration as there is for the particular application. So that's another big thing to watch, how to do this efficiently. And every element digital array actually lends itself to a very rapid calibration. If you can have a common input to every receiver in a single snapshot of data, you can calibrate everything. And then you can use that and work out ways to calibrate the transmits. So that's a type of thing that has value for the every element digital. As soon as you're in the analog or hybrid arrays, you have to kind of go one at a time through those. There's people that are looking at advances in the calibrations for analog beamforming, maybe code modulation on the phase shifters, things like that. That will probably evolve. As those things mature, we'll put those in our chips just to enable people to be able to do these things. So that's a big type of trend. The test points, I think that's a big concern, and how you do the construction of the system in a way that you can debug it. And so one of the things that happens, I've seen this time and time again, is things get miniaturized. And you have a lot of schedule pressure. Things are put together in the lab. It doesn't work, and the first thing you do is take it apart. And so being able to build these things in a way that you have sort of built-in tests. Now that's known from the semiconductor world, how to do that, and that'll have to get extended into the whole system flow. But those are all maybe just adding to trends that Tim has articulated, some of the things we see. So I'll pause there.
Great, thank you.
I'd just like to add one more comment, if we have it.
Absolutely.
The thing that we're seeing some customers do is test their systems, their radar systems, with recorded or pre-compiled complex waveform patterns that are then broadcast in real time as a test stimulus to the radar system. And because we have a line of recorder products that can record live signals captured in the battlefield arena, and or those signals can be synthesized using very complex algorithms using MATLAB, for example. We can then play those back in real time and actually test a radar as to how well it can detect a particular signature or pattern or signal type using either real world or very highly complicated, say compromised signal to noise range stimulus signals. And we see more customers being very interested in that capability.
Interesting. And so perhaps at least tangentially related, DARPA has a program called BLIP, Beyond Linear Processing, that aims at reducing AESA complexity by transferring its functionality to increase and cheaper processing power. How disruptive are these approaches to legacy systems?
Well, I think obviously anything that can be done to reduce the complexity cost of the processing element will have a dramatic effect on the overall cost, especially in phased array systems where each channel gets multiplied by a high number. The trade-off then is, well, is the processing in that reduced capability system sufficient to do the job at hand? Typically, what we see when a customer engages with us, we ask the customer, well, what dynamic range do you need? And he said, I need the best I can get, because there is effectively no target that he doesn't care about. And that's simplified, but generally what we find, people want to get the best system that they can. That is most of our customers who are military customers, and they're really interested in doing the absolute best job that's possible. And often cost is not as much of an issue as being able to see a target that they otherwise might not be able to see with less processing.
Anyone else like to weigh in on that? All right, I'll take that as a no. Subject near and dear to my heart. How is GaN technology affecting the system and test requirements? And maybe Pete, let's start with you on that.
Okay. All right. We can talk about GaN first relative to kind of the block diagram. I'll let Tim talk about the test aspects of it. But so first of all, why the trend? So there's a higher power density you can get, and so that's big, and more efficiency that tends to work off of higher voltages. It's more efficient on the power distribution, and so there's been a big trend towards that. We do those. Our competitors make power amps, GaN power amps as well. Some of the limitations we're seeing are the recovery time, particularly on the LNAs. Now, we started down a path of making LNAs with GaN LNAs, and there's higher survive power there. But there's a recovery time issue, which particularly for a radar is a problem. So there's a big blast of energy, it saturates, and then there's a spec, or at least an objective for how quickly does the system recover. And so in some cases, we found basically the gas LNAs with limiters is actually a better solution. It's surprising, but that's a case where we are at the moment in some of the parts we've provided. There's a cost size issue. The gas can be made cheaper. So if, for costs like swap, the other, swap size, weight, and power, but there's usually a C at the end of it, because people are really trying to get the cost down. And so GaN is newer. It'll come down over time, but at the moment it's actually a little bit cheaper for us to mass produce gas parts than GaN. So we still keep those both active. And maybe I'll pause there. So the whole testing, I'm curious maybe from Tim how the GaN, the trend toward GaN PNAs has affected any test equipment they need to provide.
Yeah, no, that's great. No, thanks for the leading question there. So, I mean, GaNs are not necessarily the be all and end all. There are lots of different solid state power amplifier architectures that have different characteristics and positives and negatives. For GaNs, one of the key things is that their performance varies based on their thermal conditions. The heat can distort phase. And so the testing needs to really understand at a fairly detailed level how distortions, occur and how to compensate for those. Digital pre-distortion can come into play sometimes. And excuse me, some of those different thermal conditions and the distortion of phase can be, somewhat challenging for more traditional kinds of radar applications. So, MTIs, moving target indicators, and Doppler radars, for instance. We'll see some of these GaN effects as a negative, and then phase to phase and comparing phase between multiple pulses and amplitude. These are all challenges that GaN sometimes throws at you just because of the way that the material changes, based upon what it's doing and how warm it is. And specifically on the thermals, it's still somewhat challenging to attach heat spreaders to some of these devices. And so mainly it's positive, but there are just some things that you need to go into GaN testing eyes wide open. And we have quite a few white papers on some of the testing challenges again, specifically that might be of interest to the audience that we can follow up with if they're interested in knowing more about that.
Interesting. Thanks, Tim. Rodger, from that system level standpoint, is there a preference, a lack of a preference for GaN? Are you looking for GaN-based amplifiers, or are you shying away from them?
We typically at our division here do not get involved at the very end of the antenna chain there where the GaN amplifiers or gas amplifiers are used. So we really do rely on our customers for determining exactly what their characteristics need to be. And there's such a wide range of different RF front end circuit requirements out there. The one thing that we found is there's no such thing as one size fits all, and that's why there's such a diverse range of different analog components in the signal chain, because there has to be. So I just can't speak to the specifics of differences that already have not been covered very well by these two gentlemen.
Great, thank you, Rodger. Question from the audience: will the Mimo radar and/or quantum radar drive the trends? So maybe if we could expand that a little bit to just kind of comment on any activity you've got going on with quantum radar. Mimo radar is a term or Mimo at least, being used on the commercial side of things, but maybe if you could comment on that as well from a radar standpoint. And Pete, can we start with you with this one again?
Yeah, we can. I'll take a shot at this. I guess I haven't really given much. Thought to the quantum radar concept. Right now, we're working. Everything we've described that's our quest at the moment, and I'm in the middle of putting my energy into trying to get help you guys get the best parts from us out into the world. And so I don't really have a good answer on some of the quantum. Now the MIMO and basically the whole every element digital phased array, we do see a big quest there. And it's the term you'll hear is like software defined antennas, the same way you hear software defined radios. In order to get there, people want to get to every element digital to do that. And then how this fits into some of these other terms, maybe defer to Rodger or Tim on those.
Rodger, Tim, any thoughts, any comments?
The question, yeah. So we do quite a bit in quantum. It's still in the lab, still at the stages of trying to understand exactly how some of this technology could be leveraged and to create reliable and repeatable baseline experiments, because there's still a lot of unknowns about quantum radar. It has some very interesting potential breakthroughs. We acquired a company called Zurich Technology a couple of years back, who are providing some of the core technology that research and development labs use to do quantum experiments. But we don't have anything that we can talk publicly about in terms of where quantum's going in terms of radar. It's still at the early research in the labs, and so, but it definitely is an interesting application. Everything quantum is interesting, but quantum radar and sensing at the distance holds some very tantalizing prospects, but nothing today, unfortunately, or fortunately.
Yeah, I would just say that we are starting to sell our software radio products, wideband A to D, D to A, and powerful FPGA into studies and programs that are working on quantum computing. So we have not yet seen results of that investigation by our customers, but we are certainly seeing a lot of interest in getting the various processing engines that are now available in the multi-processing heterogeneous processing devices like the AMD Xilinx Versal family, for example, and there are others coming out from Intel as well that are going to be very, very interesting to the quantum community.
Yeah, thank you for your answers. Interesting question, and I think the answers reflect sort of what we all thought, that a lot of interesting capabilities, potential, as Rodger just said, and we're kind of on the cusp of that development. So here's another interesting question from the audience, and we just mentioned FPGAs, and we've been talking a lot already about processing, but this question is it at all possible to have military radars without FPGAs? Are the current FPGAs on the market up to the task? And what does the ideal FPGA look like in the future for military radar? Any thoughts on that one?
Well, this is Rodger again. I would try to imagine what a radar would be like without an FPGA. Of course, there are some very dedicated, like for example, automotive radars where everything has been integrated. But I think the markets that we serve, our military customers, probably will continue to be using FPGAs with the high-speed data converters, like the ones from ADI, for example. But why? Because now those FPGAs actually consist, as I said before, of multiple different processing engines that can be chosen appropriately to meet the specific compute requirements for different tasks that may come about. And that heterogeneous approach gives a single product the ability to tackle different types of targets and different kinds of exploitation tasks necessary to bring the information to whoever needs to get it. So I don't see that FPGAs are going to not be used in the military radars in the markets that we're pursuing in the near future. I think the FPGAs are just going to get more and more capable, sophisticated, faster, with higher compute power, larger high bandwidth memory resources, artificial intelligence, machine learning engines, more powerful FPGA fabric, just because that's exactly what kind of operations are needed by the the applications that we see now and in the near future.
Yeah, I can maybe try to add to that, Peter Loss here. As we, one trend, there's more processing being pushed closer to the antenna. So that's a trend. And the FPGAs are getting more and more powerful. So, and that's what's used today. So it's very natural to go for those to progress the way Rodger's explained. And then you can look at what are really the other options. So we hear discussion like, can our converters go to GPUs or something like that, or other types of processors? And the answer is yes. You can do that. It comes back to what Rodger pointed out about the synchronization of all the processing, and if that can be done in a processor, I mean, from our perspective, there's no issue. Go ahead and do it. But the FPGAs are really made for a lot of parallel streaming logic, and they're made to be programmable. Now, another trend that's going to happen is as digital blocks get more and more defined, we're going to include them right behind our converters. And so this whole digital up-down converter piece you see on the block diagram, it wasn't long ago. That was all done in FPGAs. But now that it's well defined, it can be committed to silicon. And so things that are not well defined or they're continually changing, it's hard to really commit them to silicon, because then you don't want to make an ASIC and then change it. But you can make programmable blocks and digital up-down converters, FIR filters. We have FFTs inside our parts now. And so those types of things are going to continue to progress in ASIC form right behind the data converters. That'll offload some traditional functions in the FPGAs. But then, as Rodger said, everybody wants the best processing unit they can get, and they want to do the most possible, the closest to the antenna. So in our perception, we're going to help offload some things that used to be, rudimentary and are now well defined, and then the FPGAs will go off and do the next level of processing that might have been off the array. It can all be done locally. So that's a trend. And then another aspect is, at what point does an ASIC show up, and can that replace some of this? And probably the thing to watch is like the commercial world. So the commercial world, there are balances of when in base stations and those types of things they go to ASICs versus FPGAs. And if you kind of watch that and watch the volumes as these phased arrays become more standardized, and the volumes come in place, there'll be more and more committed ASIC logic. We're going to put them in our converters. But there's always some level of programmability people want. And so keeping that balance is going to be one of the quests and one of the things to watch probably for all of us as these types of systems progress.
Thanks, Pete.
And maybe, Rodger, you could probably build on that with other things you see as you put parts out.
Yeah, I very good points that you bring up. I think the configurability of the logic is really is a unique part of what an FPGA offers that can be customized then to treat different types of data converters that are out there, interface specifically to them with the interface protocols that are required, and then, as you mentioned, the synchronization that's required for each different type of data converter could be implemented in a new logic design with an FPGA. It would be very difficult to have a generic non-logic programmable device be capable of adapting to different types of data converters. As you said, the commercial markets like 5G, the MIMO antennas and so forth, those can justify volume-wise ASIC implementations. But our market, the military market, is really different in that we need to produce a certain finite number of systems, and then we need to do the next generation very quickly thereafter. And so it's a moving target driven by technology, driven by adversary threats that we have to adapt to. So having a fixed solution is just probably not in the cards for the market that we're in.
Great, thank you.
Yeah, it's a great summary.
So here's another interesting question from the audience. That's sort of a strategic philosophy question. And I'm interested in what you're doing, what you're hearing from your Defense Department contacts. What's the expected viability of a military radar enterprise that's built around a finite number of very high value point systems, i.e. targets, in a world of loitering anti-radiation weapons? Any thoughts on that? I'm curious.
Okay, so maybe just to re-articulate the question. So the value of a reduced number of ultra high power assets as opposed to maybe distributed, lesser capable assets. Is that the basis of the question?
Let's go with that. Yeah, I'm interested in your answer to that as well.
Well, I'll take a stab at it. So I guess I would talk to probably some of our customers, people that are building these systems and even defining them for the prime contractors. An analogy is how many aircraft carriers do you need versus ships that float around that are smaller and cheaper, and so that's a type of analogy. We tend to see, we think at least, there will be a lot more distributed systems of some form. And from a dynamic range perspective, even think about like these arrays. Like an array, even though maybe a large one in a centralized system, it is comprised of a set of distributed receivers and waveform generators. And you can get dynamic range benefits combining those, and people take advantage of that. We have articles that show all those things. When things are distributed and flying around, like the whole drone UAV world, it's a little unclear to us how you would do coherent integration, but certainly all the triangulation and a lot of distributed processing, and we think will proliferate, to be honest. And so I think we're not in a world really to define that. We're going to provide the parts and listen to what our customers need in terms of swap. What can you get away with as far as performance in those types of systems to get the cost and the power down. We'll adapt and we'll make these things, and we'll probably let some of you folks that are listening today kind of drive where that goes. Maybe with that, I'll turn it over to someone else.
Great, thanks, Pete. Anyone else want to chime in on that?
Yeah, so couple of thoughts on that. So we're definitely moving into an era where customers are a lot more concerned with what is an 80% solution rather than spending another 90% to get to the last 20%. There is obviously still a requirement and need for sort of exquisite applications and devices, but at the same time, what we're seeing in Ukraine is that attritable, low cost devices, swarm drone attacks, for instance, can get the job done. And so we're really, I think, considering what it is we need to do, and that's not specifically a radar thing. But some of these very small platforms, as alluded to just now, can be very useful in, for instance, doing direction finding, direction of arrival, battlefield damage assessment in an EMS operation, so electromagnetic spectrum operation, not necessarily a physical damage, but where are the emitters in the environment? Where are these things? How can we find them? And those are all really interesting and novel applications that are definitely giving us pause to consider how we conduct operations in the future.
Tim, a follow-up question for you from the audience. The question is, all panelists mention thousands of antenna array elements. What are the system level calibration challenges for a 1,000 channel phased array module?
Yeah, I can't really go into the details of that in an open session, but your large channel count arrays have a number of system level calibrations, obviously phase amplitude, side lobe suppression, main beam performance. These all require typically an over-the-air solution. And sometimes that can be done in an anechoic chamber, but sometimes at full power, these are done on open air ranges just because of the amount of power. So, full array testing can be significantly time consuming and very challenging to set up and repeat. And the repeat is also something that is on a lot of our customers' minds, is how repeatable is this from one batch to the next, given the variations in manufacturing and just in measurement, especially for over the air type kind of things. Over the air measurements have traditionally been a challenge to make repeatable over long periods of time. So yeah, I'm actually writing a white paper right now on over the air testing and calibration of phased arrays. So that'll be something coming out in the next few months that might be of interest to the person that asked the question, or the audience in general. Over.
And you and I should talk about that white paper. Now we've poked around. Did anyone else want to chime in on that? Okay. We've mentioned this, and go ahead.
Oh, I was going to just talk on the calibration. So, the calibration is a big factor in particularly these large phased arrays. And so if we break down, what are the things you need to calibrate? You need to be matched in amplitude and phase to produce the main beam, as well as any nulling in the antenna pattern is probably actually more of a limit on the amplitude and phase match, because you're trying to cancel in a particular direction. So that the calibration's goal is to match that. So in our case, we're going to try to provide the tools to make it less painful. I'm not going to say it's not painful, but to minimize some of the pain. And so in like the data converters now, there are FIR filters you can use, and that can kind of equalize across frequency. So in addition to just matching amplitude and phase, each channel is going to drift, not be the same across frequency, and each channel may have some difference. So you got to calibrate that out. So those are methods. There are phase controls in the NCOs. There's filters you can use to set up equalization, and so that's in the end what some of the control mechanisms. Now you have to do your own algorithms to figure out how to program them. But then once you're calibrated, the next question is drift, really. And so drift can be typically over temperature, but it can be other things, and vibration, or anything that can cause an amplitude and phase variation versus some other parameter. Temperature is an obvious one, but it's probably not the only one. So we're putting a lot of effort into low temperature drift, particularly on the PLLs and other types of circuits. It's going to be a type of thing to measure, probably phase versus temperature. It's not typically in all data sheets, for in the semiconductor world, but that will evolve. And so there's, I think at our level, a couple things: providing the vehicle that once you figure out what the calibration is you want, that we have the hooks, you can put it in there. And then once it's calibrated, things are stable, at least from the IC level. And then how you build the system, you have to do it in a way that's stable. And the thermal gradients across the array will be a big thing to watch. And so that's maybe some added types of things to think about without actually providing a solution that ultimately some of you folks will probably be the ones that determine how you want to do your calibration.
Excellent, thank you. Well, unfortunately, we're getting close to the end of our time slot here. So I'd like to throw out one last question to the panelists, and I'd like to start with Peter, and then we'll go kind of in reverse order. What future directions are you seeing in the market? We sometimes talk about a combined communication sensing radar system. Are we going to get there? Should we get there? What do you think the future holds? And if we can kind of limit it to a couple of minutes, I think that'll be perfect. So Peter, if we can start with you.
Yeah, I'll go first. Maybe just a few summary points. A lot of this we've spoken about. So as Tim mentioned in the beginning, there is a quest towards these multi-mission systems, combining comms, EW, and radar. That, in our view, I think the hardware is there. It can be done. It's a matter of what's the most efficient way to do it. You end up with something that's either too expensive or suboptimal for all the different types of applications. Some of the nuances of the waveform processing drive different specs, but the world is going to try to go there, and so that is a trend. And then maybe the second thing is what you can just say, these software-defined antennas, and what does that mean? That's the trend towards every element digital. It doesn't have to be every element; it can still be a hybrid, or near every element digital is another term we hear. And we see most new array developments are phased arrays, particularly in the, when we talk about military radars. And then the question is what type of architecture, bands, instantaneous bandwidths, and so on. But I would say in general, this multi-mission and software-defined antennas sort of summarizes what we'll be doing over the next decade.
Thanks, Pete. Tim, from your standpoint, future directions, and we're going to see that combined communication sensing system.
Absolutely. So just one comment on that is, the move really to being able to modulate pulse by pulse what you're doing, and leading to more of a modulated scheme changes the test requirements. So a couple of other things. We haven't talked too much about it, but there's a big requirement now to test these systems in a much more controlled environment. What I mean by that is an environment where you can create a very complex RF environment. In the past, that might have been done by doing PDW, pulse descriptor word streaming, to create that. The modern threats that we're trying to basically create and ensure the system can counter means that we're moving to higher fidelity IQ-based data sets. And those might have been captured in the wild, or they might have been created in simulation tools. But really that drives an increase in the number of emitters to create very complex environments that are representative of what you might actually expect to see in a deployed environment. And so the challenge with that is just the enormous amount of emitters that you need to creates a very complex system. But it's necessary for the second reason, which is that a lot of our customers are moving away from doing open air range testing. It's an uncontrolled environment. It's not easy to create the complexity that you might desire the end system to think that it's operating in. And then there are also concerns about eavesdropping on ranges of people that we might not necessarily want to be sitting there and looking at what is going on in a live test. Couple of other things, the increasing bandwidth and dynamic range of some of these newer technologies is leading to discussions about how the back-end processing works, and really about how data movement works. There's things like RF over optic, which are driving some new test requirements. We talked about quantum sensing and quantum radar. Final one. There's a lot of research going on in that area that hopefully one day will yield some interesting results. So there's a lot of work still to be done. Over to you.
Great, thanks, Tim. Rodger, any last thoughts?
Sure. We mentioned it before. I think the move towards artificial intelligence, machine learning, the ability to synthesize a new answer to identify a target, classify a target based on similarities to known standard library modules is really going to be helpful, because those types of signals are changing all the time. And that AI function will help the systems adapt dynamically to those new signals as they appear. I think the other thing that we're seeing is the the fact that with direct RF, which is another major trend, we're going to see more interesting RF uh, filtering before the data converters to carefully control the bandwidths of the different signals that are of interest and exclusion of signals that are not of interest. So perhaps complex multi passband filters capable of selecting 3 or 4 different passbands and excluding others. I think those are on the horizon and will help the direct RF succeed in spite of the challenge that direct RF, looking at everything, you have to exclude things that you don't want. That's going to make it work.
Yeah, great. Thank you. Well, I wish we had more time, but unfortunately we don't. So I'd like to thank all the panelists for an excellent discussion. Now, we've had a lot of questions and we've gotten to a lot of them, but not all of them. So if we didn't get to your question, the panelists have been kind enough to offer to get back to you with answers. The session has been recorded and it'll be available to watch in about an hour. You'll find it in the events section of the Microwave Journal website under the archived webinars and events tab. So please feel free to watch it again or share it with any of your colleagues who may be interested. And remember, if you aren't already a subscriber to Microwave Journal, you can sign up on our website. Now, let me close by saying thanks again to our panelists and all the audience members for joining us today. Keep an eye out for upcoming webinars and panel sessions, and I hope you all enjoy the rest of your day. Thank you.
Thank you.